to understand the behavior of free scalar fields, free massless scalar fields in 2 dimensions. So today I'm going to just do free scalar fields, massless scalar fields in 2 dimensions, which sounds boring, but there is actually some fun still to be had. As I want to describe the final purpose in the next lecture will be to pretty much understand what is the spectrum of string theory, what are the excitations of the strings propagating in space-time. So the shape of your worksheet or the 2-dimensional space over which the scalar fields live is going to be a tube. So to be precise, today we want to study a free massless scalar field in 2 dimensions on a cylinder. When the 2-dimensional space-time is a cylinder. So I take space to be a circle. Sigma will be my coordinate along this cylinder, along the periodic direction of the cylinder. And then I have a Euclidean time tau. And I put a flat metric on the cylinder. And it would be useful to have complex coordinates on occasion. I call it S as tau minus I sigma. Okay. Now, how do I study a free scalar field on the system? Well, a possibility is I just take my path integral over the cylinder. If I have some correlation functions or something like that, I just use the path integral to compute them. It's all Gaussian. That's straightforward. But because I want to study the state of this system, it's perhaps better to use a Hamiltonian sort of formulation. So I take my field, my dynamical degrees of freedom are the configuration of the scalar field along the circle. And then I look at how they evolve in time. Now, so the free boson, the free massless boson, satisfies some, essentially, has a Gaussian motion tells you that its Laplacian is 0. The 2-dimensional Laplacian is written as L del S del S bar. Okay. Perhaps I should put hats over everything because it's going to be an operator, but I don't care. Imagine hats wherever you can put them. So if I start expanding my my scalar field in Fourier modes around the circle, I get something like this. Sorry. For a moment, let me introduce the size of the circle. Let's take the space to have size L. It will be useful for a little bit to keep track of some interesting features, and then later I'll set L to 1. Also, right, as I remarked, I'm using Euclidean time. If you want to compare the formula I write with formula written in Minkowski signature. Yes? It's bar. So S bar is tau plus I sigma. So if you want to compare the formula with the formula in Minkowski signature, you might want to remember the relation between Euclidean and Minkowski time. So these are all coordinates on the surface. Okay, they're what I was calling U1 and U2 in the previous lecture. They're not coordinates in the target with the space-time.
So usually when we Euclidenize Minkowski space, we get a periodic time coordinate. So is tau not periodic?
No, that's your choice. I mean, if you want to do a system at finite temperature, you would put a periodic Euclidean time. But otherwise, you don't need to. So, okay, let me just finish the expansion. Okay, so AN and A bar N are modes which have pretty much energy N. See, they go like e to the minus N tau. Well, N over L. Now, so this is a classical expansion, if you want, of your scalar field. Now, I propose that to quantize it, you define commutational relations. On this sort. Mm-hmm.
X and P, are those the center of mass and momentum of the...
That's right. I'll...
and the other thing, when you check this commutation relation, are because you're doing somehow some canonical quantization?
A moment. Okay, so right. So how do you check that this makes sense? Well, one thing you could do is to take the Hamiltonian of your free scalar field. You plug this in, and you discover that these modes have the same Hamiltonian as some harmonic oscillators. The other possibility is that you just compute directly an equal time commutator. So use these commutational relations, plug this in. You get something like this. Okay. So this would be your typical starting point of a quantization of a free scalar field. This is the momentum conjugate to the position. Okay. Okay, so this is the basic formula that we will need in this lecture. So now a nice feature of a free massless scalar in 2 dimension is that so it has, see, this scalar has a symmetry, which is just translations of the scalar itself. X goes to X plus a constant. And to this symmetry is associated a conserved current, which is actually just essentially the gradient of the scalar field. See, because the divergence of this current is just the Laplacian of X, so it's 0. Now, if you write this conserved current in the holomorphic coordinates, S or S bar, you see that this current is actually holomorphic. So it's not just true that the current is conserved, that you would write as ds bar Js plus ds Js bar equals to 0. But actually, it's true that ds bar of Js is 0. And ds of Js bar is 0 separately. Mm-hmm. So yes. So this holomorphic derivative of x is an holomorphic function, and del bar s is an anti-holomorphic function. So what does it mean? This means, for example, that there are actually a lot of conserved currents hidden inside this Js and Js bar. because I can take whatever function of S bar I want, multiplied by Js, and this satisfies still, sorry, in function of S I want, and still satisfies this equation. So besides the current Js and Js bar, which are conserved, I get a whole other set of currents. And the conserved charges for these currents are just these modes, the Fourier modes of the scalar field. Pretty much this means that at the level of symmetries, the scalar field can be shifted by any holomorphic function you want without changing the equation, the fact that the equation of motions holds, or any anti-holomorphic function. So it's free scalar. If every free field has infinitely many symmetries, infinitely many conserved currents, and in this particular case, they take a very nice form. Okay. So essentially, the fact that these currents are holomorphic or anti-holomorphic essentially means, means that when you look at correlation functions of these currents, you find nice holomorphic or meromorphic functions. So you get to use a lot of complex analysis. Now this is tied to the fact that the action for the free scalar was while invariant. So when you have wild symmetry and diffeomorphism invariant, it's very natural to start encountering complex coordinate transformations. And things behave well under complex coordinate transformations. Now, the first thing we can compute is the 2-point function of the scalar field on a circle, or on this cylinder. Well, first I should describe a bit better the Hilbert space of the scalar field. So we define these oscillators. We had these extra coordinates x and p, which indeed are the center of mass, position, and momentum for this string, for the configuration of the scalar field over the circle. And we should define a Hilbert space too, a Fock space. And we can just define a vacuum to be annihilated by all positive energy. So all the oscillator modes which would lower the energy. So the ground state should be annihilated by everything that would lower its energy. So pretty much like for an harmonic oscillator, we could just define our vacua by the property that n kills them for n bigger than 0. Now, we also had this sort of these extra 0 modes, which behave like a whatever, this will work. Sorry. So we also have these 0 modes which behave like the coordinate momentum of a particle. So when we describe the Hilbert space of a particle, we can use momentum eigenstates. So we'll define the basic ground states of the system as these momentum eigenstates. Let me put a hat here. So starting from these states, which are eigenvalues of the momentum, of the zero mass momentum, we can build a whole Fock space of states by acting with the raising operators. So the states in the Hilbert space will look like this. So if you want to start to figure out how some of these operators act on some of these states, say if you want to compute A1 of A minus 1 squared of E, what do? Well, you use your commutation relations until these kind of operators hit the cat and kills it. So you write this as A minus 1, A1, A minus 1, P plus A minus 1P. Then you write it as 2 A minus 1P plus A minus 1 squared A1P. And then this is 0. So this is how you figure out how the modes of your scalar field act over the various states in the Hilbert space, in the Fock space. Mm-hmm. Well, so I did not write down the Hamiltonian. Perhaps I should have. But the point is that these states lower the energy of a state, while these ones raise it. So if you want to Hilbert space to have a bottom, some lower energy states and everything else is built up from them, then you need it to be annihilated by these guys. Otherwise, it would create a state with even lower energy. Yes, that's right. Well, sorry, the other way around. So this one with positive index lower the energy. And these ones raise it. Yeah, I mean, in an appropriate sense, AN and A minus N are emission conjugate of each other. But to say it properly, to talk about Hermitian conjugation, you want to go to Euclidean, to Minkowski signature, do your complex conjugations there, and come back to Euclidean signature. In Euclidean signature, you should talk about something called affection positivity, which I don't want to get into. Okay, so now that we have some vacuum, in particular the zero momentum vacuum, I wanted to compute the expectation value of these currents, of these holomorphic derivatives of the scalar field. So you just plug in those expressions, and it reduces to something like this. Well, there is a okay. So what does this mean? Let's see if we can make sense of this expression. First of all, let's take our cylinder to be very, very big. So we're actually essentially doing things in flat space. Okay? Then these exponentials become just, you can just expand in 1 over L. And this pretty much becomes minus 1 over s minus s prime squared, which is compatible with the 2-point function of a scalar field in flat space. In flat space, the 2-point function of a scalar field is Green's function for the Laplacian. So in flat space, you would expect something like, I hope I'm getting the sign right. Roughly. So if you take the derivative with respect of s and s prime, you get something like that. Also, if you stare at this expression for a little bit, you can see that this is actually the Green's function on the cylinder. So this is the del bar, del s del s prime of an harmonic function, which is periodic on the cylinder and has a singularity as s goes to s prime, a logarithmic singularity as goes to s prime. So this is quite a reasonable expression. Now, the reason I wanted to compute it is because I would like to understand the stress tensor of this theory. So yesterday, I mentioned that there were equations of motions for the. So we started the theory with some metric and some scalar fields. Mm-hmm.
When you calculate the 2-point function, the vacuum that you're putting there is not the same vacuum as the Fock space that you constructed.
I picked p equal to 0. Okay. So I took the scalar the 0 mode at rest.
What is the tilde right there?
What did I put the tilde?
The last line on
Oh, I just meant as L. If you take the L to infinity limit while keeping your point fixed. So I remember yesterday there was something involving a metric on the worksheet, and then the position, the scalar fields, which describe the position of the string. And we gauge fixed away the metric, but we were left with the equations of motion for the metric, which was something like ds over d HAB equal to 0. And essentially, by definition, the variation of the metric of an action with respect to the metric is what's called the stress tensor. Now, if you have if there's some action which is invariant under diffeomorphisms. So if your action, then the stress tensor is conserved. If your action is invariant under wild transformations, we just rescale the metric, so change the metric by a multiple of itself, then it must mean that the trace of the stress tensor is 0. So these are all classical statements, and whenever these statements get into some trouble is when you quantum mechanically is where there is a chance of having anomalies, problems with these symmetries at the quantum level. So yesterday I mentioned that the anomaly in the wild symmetry was a crucial issue when you try to define a string theory. So I would like to understand the anomaly for this free scalar field. And for that I need the stress tensor. I have to write down the classical stress tensor and try to see how to make sense of it quantum mechanically. Now, notice that in holomorphic coordinates, in complex coordinates, the tracelessness is just a statement that T, say ZZ bar, is 0. The conservation, you write it as something like this. But this is already 0. So actually, let me lower some indices. Let me write it like that. Okay. So actually, if you have a theory which is while invariant and diffeomorphism invariant, your stress tensor satisfies a pretty nice conservation relation. The ZZ part of the stress tensor is holomorphic. So this is very similar to what we had here. So this shows you that a theory which has wild symmetry and diffeomorphism symmetry, when you write it in a complex, flat metric in complex coordinates, so you see that there are infinitely many conserved charges, infinitely many conserved currents. These are the conserved currents which are associated to holomorphic changes of coordinates. But we will discuss that more in detail in a few lectures. For now, all I want to keep is the fact that we have some stress tensor, and classically it should be holomorphic, and we should make sure that these sort of properties don't get too broken in the quantum theory, or if they get broken, we should try to understand exactly how. So what is the stress tensor for a free scalar theory? In principle, we should be patient, start from the action, vary it with respect of the metric. Okay. And roughly what you get is that the stress tensor is the traceless part of a bilinear of this current, these currents. So in particular, TSS or TZZ is, let me show the holding some sign. It's minus, classically, is minus DXS. classically. Now, quantum mechanically, it's clear that this definition is a little bit problematic. Right? For example, if I look at the if I try to get the 1-point function of the stress tensor, starting from something like that and sending S to S prime, I'm going to get a divergence. So this has to be regulated. Okay. Now, whatever regularization I pick for the stress tensor should be sort of a local choice. When I define my operator, I should define it in the same way, no matter where I'm placing this operator, no matter what I'm doing to my space-time far away. So when I regularize this operator, I better do it in a way that does not depend, say, on the size of the cylinder. Now, in flat space, usually you say that you regulate the operator by normal ordering, pretty much. You take your expression, you switch around creation and destruction operators in such a way that what you get annihilates the vacuum. That is a fine definition in flat space. So it's pretty much equivalent in flat space to say, okay, I take my flat space. So I take my tentative expression. I remove the vacuum expectation value. And then I take the limit. So this is the flat space definition of the stress tensor. There's probably some 1/2 that I'm dropping. I'm sorry. Pretty sure there was a 1/2 here. Probably here there was a 1/2, I guess. 1/4. Anyway. So now in flat space, this actually means subtracting 1 over S minus S prime squared. Okay. This is the same. Now, when I'm on the cylinder, I can't quite subtract this, okay? Because this depends on the side of the cylinder. That's not good. But at the end, I just want to subtract some. I want to remove the local divergence in my 2-point function. So a reasonable definition on the cylinder or on any surface really. Is to just subtract the local divergence. Okay. Now, so this you could call this a point splitting definition of the stress tensor. Now, notice that regularizing the stress tensor is intimately connected to the notion of regularizing your path integral, to keeping track of how changes in the metric affect your regularized path integral, because the stress tensor is expected to measure the changes in the metric in your correlation functions in the quantum theory too. I mean, you want to define your operator in such a way. Now, changing an operator just by some constant doesn't affect correlation functions very much, but it affects the overall normalization of these correlation functions, or this partition functions. So when we regulate the stress tensor, if you look at it carefully, it's closely related to how you regulate the overall normalization of your path integral. This can be precise, but I don't think it's going to be very useful now. So for now, let's just compute the one-point function of this stress tensor on the vacuum. Okay. So what do we get? We get this. Mm-hmm.
So you're trying to remove the singularity by adding that term.
Mm-hmm.
But is that enough? Because I mean, that only works in the limit where the size of the cylinder is very big.
No. See, if S goes to S prime, this is the only divergence. After I subtract this, I find a finite quantity, which actually I can compute. So I need to take the limit of this. I also put a minus 1/2, sorry. Okay. So, well, that's not very difficult. You put it in mathematics, you ask to expand as S prime goes to S. I mean, this is essentially 1 over sinh squared. So there is a divergent part, and then there is a finite part, and there are positive powers of S minus S prime, which go to 0. So the answer is minus 1 over 24 L squared. So the stress tensor has a valve on the cylinder. What is the physical meaning of this? I could take the stress tensor, I could compute the energy as an integral or sigma of T sigma tau, for example. And if you do that, you'll find essentially the Casimir energy of a scalar field, of a free scalar on a circle. So this value here is intimately connected to the Casimir energy of your system. Now, in textbooks, very often they get the energy of the system just using some sort of a trick. They say, for example, they say, okay, this looks like an infinite tower of harmonic oscillators. Each harmonic oscillator gives me an energy which is n over 2, and then we sum n over 2 from n equal to 1 to infinity, we get minus 1 over 24. Okay. And then they invoke zeta function regularization, analytic continuation, whatever. So there are reasons for which these tricks work, but there is a very precise physical meaning behind. Okay, the energy is something concrete. Is related to the stress tensor. If you regulate your stress tensor in a physical way, you're going to get a reasonable answer, physical answer for your energy. Using mathematical tricks works if you use the right one, but I mean there are good reasons for which the tricks that you see used in textbooks give the right answer. it would take probably too much time to discuss it, but pretty much they are all tricks whose purpose is to, yes?
So the sum of the series, to obtain the sum of the series, you manipulate the oscillating series.
I didn't do any, I didn't do it like that. I did this. Okay. Now, what you sometimes see is things like this. You study this. This defines a nice analytic function of S for S smaller than -1. And then you analytically continue all the way to 1. And you call that the answer. That's a zeta function regularization. I know, so this doesn't make sense. Okay. Now, what makes sense is to do some asymptotics. You can put the capital N here. And then you get something like, well, I guess we could probably do it, but yeah. What was it? N plus 1. Let me see. I try to remember how you get -1/24. Like, yeah, except that. Yeah. Yeah. I had to refresh my memory, but roughly, see. Yeah, of course. No, the point. What is the point here? Here, there is in the physical calculation, you're doing regularization. You pick some cutoff. Okay, so you don't send your momentum all the way to infinity. You pick some cutoff. So your sum is going to go up to momentum modes which have a certain size. But the size should be something intrinsically defined, not something that depends on the size of your big circle. So if your cutoff is some lambda, you go to momenta which are up to something like L lambda. Okay? This has to be done correctly. I'm not doing it correctly. But the point is that when you do this expansion, and now you see how does it depend on this L and on lambda. You find something with positive powers of this L lambda. And then you find a constant term, which if you do things correctly should be -1/24. And then you get things that go to 0 as lambda goes to infinity. And then you say, oh, these things look like integrals. These are things that I can get rid of by some local counter term, by some local modification of my energy, or my stress tensor, whatever it is, integrated over the circle. And so you say, okay, in some way or another, I get rid of them, and what you're left with is this constant. So this is a very fully explained. I'm sorry because I didn't prepare the details, but this is why these tricks based on zeta function regularization or things like that give you, at the end, if you do them properly, give you the right physical answer, is because these tricks based on analytic continuation reproduce the constant part of some asymptotic expression. And then the polynomial part is removed by your regulator, can be removed by a regulator, and the constant part cannot. Anyway, we did it like this. We got -1/24. We're happy. Yes?
So why did we not want our counter terms to depend on L?
Well, so right, it depends a bit of what you want to do. But when you do quantum field theory, there is some notion of locality that one of the most powerful properties of quantum field theory is sort of a separation of scales. Things that happen at some large scale do not depend on something that happens at small scales, or depend in a very limited fashion. So you don't want your short distance regulator to depend on what's going on far away. Now, perhaps, right, if this was an an effective field theory. So if you had some other system, like a lattice, at small scales, and then this is an effective description of it. So this regulator would some sort of account for the difference in the definition of the Hamiltonian in the continuum and in the discrete system. And again, this difference has to be the integral over the circle or something local. Mm-hmm. No, I didn't. So the vacuum extension value of S is one way to compute the energy. Another way to compute the energy is just start from your original Hamiltonian that I did not write, which is something like sum of n, an, a minus n, or something like that. So a sum of Hamiltonians of harmonic oscillators. And the 0-point energy of these harmonic oscillators. So, okay, so pretty much this was the only reason I was keeping L until now, to show you why this subtraction is a reasonable thing to do. So from now on, I just set L to 1 and forget about L. Now you can already see that the regularization is going to give you some funny features when you try to conform, when you try to do changes of coordinates, holomorphic changes of coordinates. Let me elaborate on that a little bit. Now, suppose you're studying some correlation function of just scalar fields. Okay. So this correlation function somewhere, doesn't matter where, cylinder, plane, some Riemann surface, I don't care. Because of this is just a Gaussian theory. This is given by some weak theorem, right? So you start doing weak contractions, you get some sums of products of 2-point functions. And these 2-point functions are just the Green function of the Laplacian operator. Crucially, this expression is pretty clearly invariant under nice coordinate transformations. Okay. So if you do some coordinate transformations, if you send your S to some S prime, which is a function of S, then your scalar field, all that happens is the correlation function of the scalar field is that the arguments of the scalar field change. So it means your scalar field can be identified as x of S prime of S. Well, maybe I should put some primes like this.
You're saying that you don't care about the manifold where you're working on, but still the Green function will depend on that, right?
Yes. The Green function will depend on that, but it's a function.
Right, okay,
So it means that if I change coordinates, the function transforms as a function without any fancy behavior. If I have x, the function is S squared, I say that S is S prime cubed, then the function becomes S prime to the 6th. You plug the coordinate transformation inside the function. The first derivatives of your scalar field will transform like 1/4. So there will be some Jacobian. So this is all pretty uncontroversial. Now, what happens to the stress tensor? So this part transforms fine. So you get one of these Jacobian factors here, one here, no problem. But this part does not transform very nicely, right? So it means that if I try to understand how the stress tensor, the quantum stress tensor is related in some coordinate system or in some other coordinate system, so I will get something like ds prime over ds squared, which comes from this transformation. But I need to do something about that. So in a sense, you get something like this. You get so let me make sure that I'm sorry, too many primes. Let me call this new coordinate tilde. Okay. And I'm sure I get the algebra a little bit wrong, but bear with me. Okay. I would like to say that I should get something like this. Well, I need a limit s prime to s. I get something there, tilde over ds, there's tilde prime over ds prime, 1 over s tilde minus tilde prime squared minus 1 over s minus s squared. Oops. Now, the divergence of these two functions is actually the same. So this difference is finite. Well defined, but it's not 0. So feel free to take this, expand it in powers of s prime minus s, and see what you get. You get some ugly-looking expression. It's called the Schwarzian derivative of s tilde. So roughly you get something like this. No, I just write it as now, so you see, the stress tensor is not transforming quite right. Okay, you say, okay, whatever. Problem is that, see, the stress tensor is supposed to be the change in your correlation function, so partition function, when you change the metric. See, so if I change my metric by some delta H AB, the effect on partition function or correlation function should be the same as inserting a TAB del H AB inside. Now, if I try to write this in different coordinate systems, you know how the metric changes? It has some Jacobian, which is exactly the opposite of this. So this is fine. But this one is not. So you see that somehow you get some tension, some slight problem with coordinate changes of coordinates. Now, when I say changes of coordinates, these are really changes of coordinates together with a wild transformation, because here I did a calculation in some holomorphic, essentially with a flat metric. And I'm using, in fact, I can do a change of coordinates and then a wild transformation to go back to flat metric. So this number here represents to this term encodes part of the problems that this theory has with wild symmetry. So it's actually possible to argue that, whatever classical theory, which is classically while invariant and diffeomorphism invariant, is going to have problems that look like this with some different number here called the central charge. So here, so this the scalar field has a problem of magnitude 1 with wild symmetry. Now, this pops up in a lot of places, although to see why we had to think about it better in some other lecture, the fact that here there is a non-zero Casimir energy is also tied into that. And there is another nice manifestation of this, which is the last thing I want to do today. Actually, admittedly, we are a bit short on time, but so yeah, by the way, so this sort of expression over there, I could have also written by saying that T is minus 1/2 the naive normal ordering minus 1/24 L squared. See, the naively normal ordered two-point function is something that essentially by definition gives you 0 once you put it in the expectation value. And this minus 1/24 accounts for the difference. So if you actually expand the stress tensor in Fourier modes, you get something like this. Okay. Is convenient to denote it like this. Okay. So these are the Fourier modes of the stress tensor. As I mentioned up there, these Fourier modes are actually the conserved charges of some symmetries. I'll leave the discussion of what symmetries those are for later, but they're roughly just coordinate transformations, complex coordinate transformations. All I wanted to do in the remaining 20 seconds is to compute the algebra satisfied by these modes. Okay. Now, you can do it. You can try to do it directly from the definition, but there are some infinite sums that are a little bit bothersome. A nice way to do it is to first compute how these modes act on the operators, like the stress tensor, like phi, like x, and then expand the operators in Fourier modes. Yes? Sorry, you're right. Normal ordered of AN AM is AN AM if say M is positive, and AN if M is negative. Yes.
The sums you're summing over all the integers, right?
Yes.
Negative and positive. So, but we still have the 0 modes.
Sorry, you're right. Sorry, I was being too much in a hurry. I forgot to give us a definition. you see, because of that expansion of the current over there, it's actually convenient to define A0 equal to P and A0 bar equal to minus P. Okay. So here there was a contribution from P. For example, if you look at L0 on P, you get something like P squared over 2. So L0, in general, L0 minus 1 over 24 is the energy of your state. Now, first of all, you can start from the definition and check that Ln AM gives you M AN plus M. Okay. So in particular, L0 measures the energy of your states, of your operators. Then you use this commutation relation to assemble back the current. And you should be getting something like this, which, if you stare at it for long enough, it should be resembling the action of some diffeomorphism, some coordinate transformation on X. Well, right, you don't need to stare very much. If you sort of integrate back, you get. So you see L is acting like a vector field over your scalar. Now, what I want is the action of L on the stress tensor. So for that, you essentially use this expression over there to compute Ln dsx s ds prime x of s prime. Okay. So you get I ds e to the n s ds x s prime x of s prime plus I ds prime e to the n s prime ds x d s prime x of s prime. Now, here and here, there are divergences, but it turns out they actually cancel out as s goes to s prime. So it means that this expression is a finite limit as s goes to s prime. So I can learn what the commutator of S, L, and the stress tensor is. Sorry, my shoes look like derivatives. So this is another of those 1 over 12 that come out of regulating some infinite sums if you do it by directly commuting the Virasor generators. But if you do it by just from the definition of your stress tensor, which will be the limit of dx d prime x as s goes to s prime, it just pops out from some Taylor expansion. Okay, so now if we expand, again, there is some physical meaning for which computing the correlator directly might not be the best idea, in the sense that when you set commutators in path integrals, they are naturally sort of time-ordered operations. You put one operator and then the other, or vice versa, and then you try to take the time difference to 0. When you put the operators separated by a bit of Euclidean time evolution, that gives a regulator. And then, so when I do a calculation like that over there, just by introducing the S and S prime dependence, I'm putting in this regulator. I'm putting in this time dependence on Euclidean time. And again, it just so happened that that regulator has the same effect that you will get by applying some zeta function regularization or something like that. Anyway, so the final answer, sorry for going over time. Okay, so this is the so-called, what's called the Virasoro algebra. So if you ignore this is just the algebra of those vector fields, e to the ns d over ds. But there is an important quantum correction, which is again this 1 over 12. And if you elaborate a bit on the relation between, on the fact that these L's are acting as coordinate transformations, you can actually tie up together that expression over there on the top board with this funny curly bracket, the Rosen derivative, and this. So these are all proposals for exercises to take home. Okay, any questions? That's right. Is the conserved charge for another symmetry. See, L0 has to do with e to the 0s ds. So L0 is just translations. Actually, it's time translation plus I rotations. So that's why it's the energy. Actually, yeah, sorry. It'll be a bit